Hello, class. So this is the extra video that I said I was going to do, which you're not required to watch, but you can watch if you want. And the point of this video is to explain where does this formula for the average value of a function come from. So what I told you that this average value means is on average in this interval, this is the value the function takes. And I kind of drew a picture, and let me draw it here again. Suppose we have some function here. Let's say we're in the interval a to b. So this is a, this is b. So we have this. So I mentioned that you're really just taking an average with infinitely many points. So if I'm going to just draw a couple points here. So let's say we take this point here, this point here, this point here, etc., some point here. Right? And you're adding all of them and then just dividing by how many points you chose. Right? So it's really just an average. The thing where the calculus comes in is because we're doing this with infinitely many points. Right? So the only way we can deal with infinity is if we take limits. And so what we're going to do first is we're going to divide this into n subintervals, kind of like if we were trying to approximate this. So let me divide this into subintervals. This is the first subinterval, the second subinterval, the third subinterval, all the way to this. All right, so this is we pick a x value here. Let's say we pick the x of 1. Let's say this x value for that function value is x of 2. This one was x of 3, and then all the way. And here we have x of n. Right, so we have n subintervals. And we evaluate the function value at these subintervals, and those are the function values, right? So for example, this point here would be f of x1, this would be f of x2, etc., right? And this would be f of x sub n. So if we have finitely many terms, we can easily find what the average is, right? Because we could do a finite average, or we could define this to be just add all of these, right? So f of x1 plus f of x2 plus all the way to f of xn. So we're taking n numbers, right? And then how do we take an average? We divide by n. So that's the average in the finite case, of course, if I have finitely many subintervals. Now, let's assume that all of these subintervals have length changing x. So like they usually have. So say each of these has length changing x, so changing x for all of them. And then, of course, our changing x is always just the length of the interval divided by how many terms we have. How many subintervals? So in this case, it would be b minus a over n. And then I'm going to write this average using a Riemann sum, or not a Riemann sum, but a sigma sum. So with sigma notation. So I'm going to write this average as just the sum, k equals 1 to n of f of x sub I. And then we're dividing by 1 over n after we add all that. Okay, so that's what we have in the finite case. Okay, this is the average. Now, again, as I mentioned, we want to take this to the infinite case. So how are we going to take this to the infinite case? So let's add a page. So for now, our finite average is 1 over n times the sum, k equals 1 to n of f of x sub I. K, sorry, k is the index. Let's use k here. Let's see if I wrote, yeah, so it should be k. Now, if we want to have this as an average that takes infinitely many terms, then what we're going to do is just as if we were trying to find the definite interval, what we're going to do is take the limit as n approaches infinity. Why? Because we want to have infinitely many subintervals. Because if we have infinitely many subintervals, that also gives us infinitely many x values where we're going to evaluate the function. So the idea is we come here, take the limit as n approaches infinity of this average. So 1 over n times the sum, k equals 1 to n of f of x sub k. If we can somehow give this this expression here some sort of finite value, then that would be an average, right? Because really what we're doing is we're taking this finite average and doing it over infinitely many subintervals. Now the trick how we're going to do this is that we're going to note that, of course, changing x we saw is b minus a over n. what we're going to do is we're going to solve for n here. Because here what we have is the term 1 over n. We're going to write 1 over n in this way. Because from this, what can we do? We can divide both sides by b minus a. If we divide both sides by b minus a, this is what we get. So we can replace this 1 over n, and again, we're not taking any limits yet, right? We're just working with without taking the limit, just like if you would using the definition of the definite integral. We're just going to replace that 1 over n with that expression that we found. Now I'm going to rearrange things a little bit. This 1 over b minus a that we have here, that's a constant, so we can move that out of the limit. So I'm going to write 1 over b minus a, since the limit as n approaches infinity. And then I can move this change in x inside the sum, because again, this change in x is a constant, right? It's just some whatever value it is. It doesn't depend on anything right now. So I'm just going to move it inside the sum. So I'm going to rewrite this as the sum, k equals 1 to n of f of x sub k, change in x. Now, what's the point of doing this? The point of doing this is that if you look at this here, this is by definition the definite integral. And we know it exists because our function f is continuous, which is the same as integrable. So writing things this way, this whole underlying thing becomes just the integral from, by definition, of f of x dx. And that's where the formula comes from. So you see, it makes sense to think of this as the average of the function, this interval, because what did we do? We took the average first by taking finitely many subintervals, and then we took the limit as n approaches infinity, which is the same as saying we're taking this average, but now we're doing it over infinitely many subintervals, which is the same as saying we're taking infinitely many functions of infinitely many function values. And of course, it turns out that we can rewrite this in a nice way to get something that actually makes sense. And that's where this formula comes from.